participant in your learning experience?
Yeah, look.
Okay. So, just so the cobwebs come off, what's the molar mass of copper? 63.5. So, 63.5. There I go, using green again. 63.5 gram per mole. And sodium? About 23.0 gram per mole. And the oxygen molecule? 32.0 gram per mole. And the carbon dioxide molecule? Do we not get the carbon dioxide? 44? 44.0 gram per mole. And copper 2 nitrate, did we get this far?
No.
187.5, let's go 188 gram per mole. Sounds about right?
Yeah.
Okay, cool. So we all, if you know how to find gram per mole, give me a thumb up. If you want to talk about it some more, wave your hand around. Cool, because I don't really want to do this practice again. So there we go. All right, so 2 moles, okay, 3.4 moles of O2. Very simple T-chart. Okay, so very simple T-chart. We're just going to go 3.4 mole O2. Okay, what's next?
Bringing it down.
Bring it down. What are we bringing down?
1 mole.
We're bringing down 1 mole of O2, and we're going to convert that to how to get grams? 32. This is what we did in September. 32 grams of O2. Okay, so we've probably done this 30 times already. So pretty simple stuff, right? Gram to mole. Okay, we can do this. We can multiply across.
108.8.
108? Yeah, that sounds about right. 108. So 108 gram O2. Now, whatever we end with our answer is going to be whatever in that last box. Gram of O2. That looks like raised to the G. Gram O2. This is stuff you can handle, right? Okay. And we can do moles and mass and all that. We can do, this is all stuff we did in September. I don't want to spend more time on it. I want to move on to something else. All right. Minecraft! Yeah, we have a Minecraft activity later on. This week. Pretty deep. All right. So before I show you this, let's talk about Minecraft. Remember we were 9 years old playing Minecraft? Wow, it blows me away that Minecraft is 11 years old. So let me ask you this. You're gonna make sandwiches, pretty simple sandwiches for the homeless, because you know the homeless, they want to eat, and your sandwiches are very simple. They require 1 slice of cheese, 1 slice of meat, pick whatever meat you like, and 2 pieces of bread. Okay. And you're going to take them downtown Las Vegas, and you're going to hand them out, and they'll be like, thank you. So if you had, guys, if your ratio was 2 bread to 1 meat to 1 cheese, and you had 5 meat and 5 cheese and 8 bread, how many sandwiches could you make?
You can only make 4.
You can only make 4. Okay? You get the general idea?
Yeah.
So a mole ratio will tell you the ratio of your ingredients. And the thing that gets used up first is called the limiting reactant. A limiting reactant is the thing that gets used up first, and once it's gone, things stop. You're like, I made 4 sandwiches, now I can make no more sandwiches.
But you can still eat extra cheese and meat.
Yes, you could. Yes. So when you made your sandwiches, you're going to make 4 sandwiches. The bread is going to be your limiting reactant, and the meat and the cheese are going to be what's called excess. E-X-C-E-S, E-X-C-E-S-S, excess. You're like, that was excessive. That means that was too much. Okay? So the thing that gets used up first is the limiting reactant, and the thing that it has extra is excess. Chase, are you with us? No, Chase. But the fun thing is, you guys are, I can just say ace, and you'll be like both of you. Yeah. Okay, so how many iron pickaxes can you craft with 12 iron ingots and 10 wood sticks? So the first thing we should do is, we're like, that's easy. I play Minecraft. I am good at Minecraft. So guys, focus. So write a balanced pickaxe equation. Well, it looks like we're going to need 3 ingots plus 2 wood to make 1 pickaxe. 3 ingots plus 2 wood makes 1 pickaxe. Make sense? Okay. And we've got 12 iron ingots, and we've got 10 wood sticks. If the iron ingots were limiting, how many pickaxes would we make? 4. Yeah. If the iron ingots were limiting, we're going to make 4 pickaxes. If the wood sticks were limiting, how much would we make? We would make 5. And that's the clue on determining a limiting reactant. Whichever reactant makes the least product is the limiting reactant. Does that make sense? Yes. Whichever reactant makes the least product is the limiting reactant. So you're crafting your pickaxes. I don't know why you need a whole bunch, but you're crafting your pickaxes, and you make 4 pickaxes, and you're done. So you would say the iron ingots are limiting, and the wood sticks are excess. Capiche? Verstehen? See, that's the question. That's the thing. So the question was, is it whatever's the biggest one? No, it's totally not. It's not whatever you have. It's not whichever one is biggest. It's not whichever one is smallest. You have to apply the ratio. Because over here, you had 8 bread, but it turned out to be limiting. It's not whatever is biggest. It's not whatever is smallest. It's whichever one gets used up first in the ratio. All right. If you like things written down, there you go. If you want to take pictures of definitions, there you go. I'd rather you learn, basically in your own words, but limiting reactant gets used up first, determines the amount of products made, and excess is left over. All right. If this concept makes sense to you, give me a thumbs up. If you want to talk about it some more, wave your hand around. Okay. Now we're going to just do mole-mole conversions. This is probably where we're going to end today, doing mole-mole conversions. Whenever you're ready. I'll just be over here erasing the board.
Cannon, be quiet.
Yeah.
Great. How many moles of chlorine gas are required to make 3.4 moles of copper to chloride? Well, we don't. Does anyone know what the ratio is right off the top of your head? No. We got to come up with a balanced chemical equation. So we're going to add some chlorine to some copper, and we're going to make copper 2 chloride. That's copper 2 chloride? Yeah, copper 2 chloride. So that's our chemical equation. Why does chlorine have to be Cl2?
Because it's diatomic.
It's diatomic. Is copper diatomic? No, copper is just plain old D block metal. All right. So go ahead and balance this. And your balanced reaction gives us the mole ratio. Ta-da! It's balanced. Yeah. So the mole ratio is 1 copper, 1 chlorine to 1 copper chloride. Make sense? So it would make sense then if it would make sense. It would make sense then that if we wanted 3.4 moles of copper chloride, how many moles of chlorine would we need? 3.4, right? Because you could be like, I want 3.4 moles of copper chloride, and for every 1 mole of copper chloride, I'm going to require 1 mole of copper, or sorry, chlorine. 1 mole of chlorine. Okay, so that's how we'd set it up. I got 3.4 moles of copper chloride that I'm looking for, and for every 1 mole of copper chloride, I'm going to need 1 mole of chlorine. Simple?
Okay.
We can multiply by 1, divide by 1. If this is simple to you and you get it, give me a thumbs up. If you want to talk about it some more, wave your hand around. Okay? Yeah, let's move on. Determine the moles of oxygen gas released by the decomposition of 5.6 moles of water. So now we're back to our 2H2O. Breaks down into 2H2 plus a single O2. How many moles of oxygen are released by the decomposition of 5.6 moles of water? 5.6 moles of water. Now write down the mole ratio. Because what we want to convert is moles of water to moles of oxygen. Is it a 1-to-1? Is the ratio 1-to-1? No, it is not. Because if you look at the balanced chemical equation, there's a big fat 2 in front of the water and a less fat 1 in front of the oxygen. So what number should I put down here?
2.
A 2. And what number I should put in here?
1.
A 1. So how many moles of oxygen do I get when I break down 5.6 moles of water? How much oxygen do I get? 5.6 divided by 2. Sounds good. That's 2.8. How did what happen? The breakdown? Okay. Excellent question. So the question was asked, and the answer is, the mole ratio, it comes from the balanced chemical equation. There's a 2 in front of the water. The coefficient in front of the water is 2, and the coefficient in front of the oxygen is 1.
Why are we ignoring the other 2?
Because we don't care about the water just yet, or the hydrogen just yet.
Okay.
We're focusing only on how much oxygen will be making.
Oh, okay.
Yeah.
If we were converting this to hydrogen gas, would we do this as a 1-to-1?
Yes. Yep. If we were doing hydrogen, it would be 2 to 2. Okay, are we good here? Do you understand that?
Yeah.
If you understand this, give me a thumbs up. If you're like, wave your hand around. All right, one more. I think one more. All right. Calculate the moles of water created with 3.6 moles of aluminum hydroxide react with excess hydroiodic acid. Oh my goodness. So first thing we need to do is figure out what the reaction would be. We have aluminum hydroxide, which is Al and OH. How many OHs go with a single aluminum? 3, good. Remember that aluminum is +3 and hydroxide is -1 each. So there's our aluminum hydroxide. It is aluminum hydroxide, right? Okay. And it reacts with lots and lots of hydroiodic acid, which is just AI. What kind of reaction is this?
Synthesis.
No.
Double replacement.
Double replacement. Yeah. I think I owe Andrew a couple of Tootsie Rolls.
Oh my god, you're getting a lollipop. What?
Is he trying to make weight? Okay. Okay. Wrestlers, relax. You're like, sugar! Ah! All right. So, this is a double replacement reaction. Guys, this is a double replacement reaction where the hydrogen is going to swap places with the aluminum. What's going to be one of the products? HOH. And what's going to be the other product?
Aluminum iodide.
Aluminum iodide, ALI, and it's going to be 3. Okay? So that's our chemical reaction. That's what's going on. Aluminum hydroxide is going to react with hydroiodic acid. It's going to make water and aluminum iodide. Is this balanced? No, because without it being balanced, we can't do the mole ratio, so we have to balance it. So go ahead and balance it, if you wouldn't mind.
Sorry.
All right. If you think you have it balanced, what number should go right here? Show me your finger. What number should go here? Looks like a 1. What number should go here? Looks like a 3. Okay, I think 3 is the consensus. What number should go here? 3, a 1, a 1, a 3. Okay, 3. And what number should go here? A 1. Okay, so let's check our work. 1 aluminum. 1 aluminum. Please don't talk while the instructor is talking. 3 hydroxides. 3 hydroxides. 3 hydrogens. 3 hydrogens. 3 iodines. 3 iodines. All right, so we have our balanced chemical equation, which is great. Now we're going to use that balanced chemical equation in our mole ratio. What should we put in our top box?
3.6 moles of hydroxide.
Good. 3.6 moles of ALOH quantity 3. It's really easy exercises when they give you a single number and they say what is or how much of something else. So read your exercise. Most of your word equations are going to be this. Here's a single number, how much what is. Okay. And now it says calculate the moles of water. So our goal is going to be moles of HOH. What do I need to bring down here? Moles of ALOH quantity 3. And then we just slap the mole ratio down and do some math. If you understand why I had to write ALOH quantity 3, give me a thumbs up. Okay. If those who don't, whatever was here, whatever unit is here, moles ALOH 3 needs to come down here. Because I'm going to have to convert. I need these units to cancel out. So whatever is here needs to be here. And if you understand why the moles OH, okay. Say by the bell!